So my biological clock says I should be reading a bedtime story to my kids now, and I hope that they fall asleep. I hope you don't fall asleep now. I still haven't had coffee after lunch.
Well,
you had, which is anyway. So
what time is it?
it's close to 9, I think, in the evening. Yeah, so
8:37.
so I'll try to catch up a little bit. Dan opened today with the DMM AI framework, and I'm taking the position of a telco. Yeah, it's a comfortable position to some extent, because you can say we don't care about the nitty-gritty little details in these AI components. We have a system, and we need to make sure that the system runs stable and according to what we expect, yeah, and to what we need to provide our customers. And yeah, bear with me if I'm a bit naive on some points here, because this comes from this position, yeah, that we take a step back and that we try to look at it on a systemic level. And that leads to a couple of observations. So yes, we're going to add AI components to the system. I mean, this is apparent also if you look at the ORAN standardization. There's a lot of space for this in the near real-time and the non-real-time RIC. What do they do? Yeah, in the end, okay, it could be an XApp that we install for a certain purpose. It could be an RF and so on. How do they interact with each other? What data requirements do they have? What load do they generate, and so on? And then there comes an immediate question to us: how do we make sure that they even cooperate, that they don't misbehave, that they really don't cause any conflicts? And this is kind of one maybe trivial observation, but if you have a system that is hierarchical and you add AI components on several levels, that in the end can control the same switches, if you want, yeah, maybe with different intentions, one looking for energy optimization, the other looking for QS improvement for certain services, certainly this can lead to a conflict. And not just coming from different hierarchies, so to say, between non-real-time and near real-time, or even there's this motion of DApps, I think, in the real-time domain, more or less. But also, if you look at it from even on the same level of height, so to say, on the same hierarchy, yeah, you can have AIs here, maybe in different near real-time rigs that are neighboring and so on. And then if you have a mobile moving from one area to the other, and they have different intentions on the left and on the right side, this can, of course, again, create conflict. And the question is, what do we do with this, and how do we handle this? So one part of work that we have done is to work with app tandems, and this is something looking even into the standard. How can we standard compliant build such a solution that does energy saving by turning off cells or layers, depending on or depending on the state, so the number of mobiles active in the region and so on, and then sending, and it's basically an app tandem having an RF in the non-real-time rig, giving policy updates to the near real-time rig where we have an XApp that effectively then can make cells move out of the, or move to a different layer, or to a different gene of B and so on. And the reason for this is on the higher layer, so on the non-real-time rig, you have time to think about things, basically. You have time to process large amounts of data. You have time also to collect data from different locations, not just one near real-time rig, but several ones, if you have several ones attached. And at the same time, on the lower layers, on the near real-time rig, you don't have much time, but you're in the closed loop that you can guarantee QS parameters, for example, for certain services, which would not be possible on the higher layer, on the higher level in the hierarchy. So in this example, this is something that we have been building together with Remeda Labs, a Polish startup company. It's kind of a tandem. So they're co-designed. and they work together. And everything in here can be built standard compliant, which is not easy because if you look at different options, how the different apps interact, you'll soon also find that the ORAN specification still lacks some interfaces when it comes to collecting data, when it comes to controlling certain aspects, which is also part of this work to kind of see where are the loopholes that we still need to fix to make it effectively possible to deploy apps that fulfill a certain requirement. Another example, and this is work we did with Northeastern University, is to really kind of have conflicting apps. Yeah. So in this example, we have two apps, X apps. One is trying to do throughput maximization. The other one is trying to optimize for energy. Yeah. So to save energy. I mean, it looks like a trivial example, but this was all built on this emulator there with real apps. And then if you look at the plot, you can see when only one of the apps is active, it has an effect, of course, on the throughput, but it's stable. Yeah. So certainly the energy saving app would reduce the number of PRBs attributed, so you can switch power down at certain intervals and so on. If they're both active, you create a state that is not stable, and then you see that the PRB attribution is going from high to low all the time, so that in the end the performance of the system is degraded somewhere, and you see a very wide variety in the throughput in the end, and variation in the throughput. And this is an issue if we really think a couple of years ahead, saying, okay, this is our network. That's a cool startup. They developed a nice X app that saved me, I don't know, 50% of the run energy magically. Yeah, let's install it, and then suddenly all my services go down, or the customers complain because they don't get any throughput and so on. So how do we cope with that as an operator? And I mean, trivial choice would be, okay, we just select one vendor. Yeah, I mean, we had this discussion earlier. Tracy from AT&T was saying this. As soon as you start up, it gets complicated, yeah. But it also allows us to use a couple of benefits then. In this work also, to be a bit complete, is a bit of a research also, how we can build a kind of a catalog to identify which apps would have conflicts, direct or indirect conflicts, because they kind of control the same parameters in the network and so on. I'm not sure this is the right solution in the end, which is scalable from an operator's point of view, because you would need to assess all possible combinations of all variants of all apps that are maybe not even deterministic, because they are AI components. Yeah, we just heard about retraining and so on. So what happens if the behavior of an app changes? Then maybe the catalog isn't right. Yeah, we install them. We say, okay, we've tested it, but suddenly the network misbehaves. Yeah, not in the way that we intended. And you probably know this from the BAU. So we had a conference. Dan was also there a couple of weeks ago. Why not take this step back and start looking at this kind of from a, we call it botany, like we assess plants, to look at an AI system or a telco system by describing it from appearance and phenomena that we observe, cluster and relate, and try to make sense of it. Yeah, there's a lot of reasons why this is not accurate, because we're kind of losing the information we already have about the system. Certainly AI does not go like plants, but there's also a good number of reasons why we think it's worth trying. Because in the end, what we foresee is that in a telco system, in the end, we will have a zoo of interacting capabilities that we don't know in detail what they do. And especially not deterministically, right? We will have multi-vendor environments. So if we have an empirical description, That would be the only way to model it. And certainly, we need to look at it from a coarse-grained level, because in the end, it's a techno-economical decision. We have a system, we have a network, we have resources distributed physically, we have connections between it, and it's not easy to just say, okay, now everything we do push to the edge, because maybe we don't have space there, maybe we don't have compute there, maybe we don't have the transport capacity to do everything centralized and so on. So there's big restrictions also that we need to take into account. And then also security is an issue. Yeah. I don't want to go too much into detail, but certainly to do this, we need to be able to describe all the system aspects. Yeah. So one part is the resource consumption, so to say, computational weight. So how much do we need for training? How much do we need for inference? In terms of to be defined computing resources. Where do we have data? How much is it? How much do we need to transport? From where to where, and so on. We need to look at the latency that the system, so transport and so on, induce. And we just heard a good talk about how we can also use AI to model and estimate the transport latency and so on. But this we need to take into account here. And then, of course, also, and this is where the conflicts come into play, what action space do the individual components in the tech system actually have? Yeah. So where do they affect? Do they affect locally? Do they affect regionally? Do they affect system-wide? And just to give you an idea on how big this challenge is, so Heiko, our tribe lead, usually likes to say that an ORAN telco system is more complex than what's it called, weather prediction, because we're looking from millisecond level on the scheduler to 10 years of investment decisions when we buy new equipment. And this is orders of magnitude higher than you would have when you try to predict tomorrow's or next month's weather. And I mean, the cluster is clear. So for the top part and the relevant part, I think for the discussions here, it's also what we see in ORAN, yeah. So from millisecond, sub 10 millisecond, and to second level and to hour level. And the other spaces, we have the disaggregation space, yeah, that we have nicely in ORAN, and then we have the discussion for optical, where you said they are not there yet, but maybe we'll get to a similar logic at some point. To the physical level, yeah. So in the real space, you have antennas, you have the distribution, and then in the middle, basically, we have the network space, which is a logical space. And if we map all of this, or if we are able to describe this, then basically we can come to, and this is kind of the wish, yeah, to a methodology where we can describe and optimize under a certain set of restrictions that we have to deploy AI components and to also control that we don't run into issues like interfering components, and that we also respect that we have a limited amount of money, that we have pre-existing infrastructure, that we have requirements, services incurred, that we have restrictions on latency and so on. And in the end, yeah, ideally, this all boils down to an optimization problem. Certainly, it's not easy to solve it and to even formulate it in a closed form, but this is our ambition, to start filling in the gaps, to get closer to being able to solve it, or solve it under a certain set of preconditions. Yeah, and this is basically the message I'm giving. Yeah, apart from the work we're doing, and also this is something we're trying to bring in Excel, this mapping from AI capabilities to techno-economic restrictions and so on, and how do we really apply this, and how do we build the framework to what we can actually deploy in real world. As an operator, you have to think systems, not individual functions, because in the end it matters that the system works. That's it.
Questions? So to do or not to do, right? Should we? You had pros and cons. I'm always curious to hear from somebody who has a lot of experience with the data itself. I'm skeptical because there are so many different situations that we cannot capture easily. So anyway,
I mean, what's the alternative?
that's true.
Not doing anything. Yeah, to be fair, solving this is impossible.
Yes.
Yeah, I mean, in a real system, yeah, maybe in a small environment, if you define this network with closed borders, you could do it. But in a real network, it's impossible. But what we expect to get from this is guidelines, if you want. Yeah. So where does it make sense? Where is it possible? Where are the boundaries? It's like in a lot of scientific work, you're looking for the boundaries first before you start approaching them step by step, right? So if you know there's a hard boundary, it's maybe not worth looking beyond it, but to confine it also a little bit. So.
But isn't there a simple way to go here in that we know how to solve the problem? It's to have one vendor provide you with all the apps, okay? And they optimize all their apps to all work together and everything. But that's the starting point, right? And then the question is not how do I get all these infinite number of different combinations of apps to work together. The question is to figure out what flexibility do I want to allow going away from that single vendor app solution, right?
I mean, there's plenty of reasons to move to an open system or to an open ecosystem, rather said. But apart from the pure having an alternative, I would say you would have to trust this one vendor that the solution is optimal or somewhere close to optimal or even good or better than somebody else's. Because you cannot really look into it, you cannot change a single parameter in the end. I mean, yeah. So, no, but it's the price we pay, yeah, for not following one closed shop solution. We get something in return, which I would say is the flexibility to explore further and to get to a better state in the end.
Maybe another way to, and I'm thinking of this, tell me if I'm wrong, but maybe the network operator's role is changing in this new model where your job now becomes how do I select the best set of apps to work together in the best way and optimize my system, right?
One precedes the other, I would say, because currently we cannot do that. Yeah.
Or I feel like you're saying you guys have to come up with a way to make your apps work together so that it'll optimize my system and I don't have to know anything and it'll just be great. Maybe another way to look at it is that you have to become an expert at figuring out how to choose the right combination of apps to optimize your system.
No, absolutely. I mean, it's not the intention to make all you guys do the work here. Yeah. It's work we're doing, actually, because it matters to us. Yeah. To know what's happening in the system, to know which state we're in and where we could move. Yeah.
That's the opportunity for you.
Absolutely. Necessity, I would say.
Okay. Okay. We should move on. Thank you.
Thanks.